I would like to give you a brief introduction into gel-derived protective coatings and what we developed and our first results from the laboratory and the results from the demonstrator. Well, the aims of our work package were to develop a gel-derived protective coating that is compatible with anti-mic, to integrate the microorganisms into the coating, to check the performance and to evaluate it in the laboratory scale, and after checking that the viability of the microorganisms is okay, our last aim was to upscale the material and to test the whole concept in the demonstrator. We used gel-derived materials, and the main benefit is that gel materials have very good protective properties as coatings. They are high stable inorganic materials with good mechanical resistance that don't degrade in the sun or at low temperatures. Sol gels can be tailored and adjusted in a very wide range, and this is very interesting because when you have a basic system and you have new issues, you can adjust your material to nearly everything. Like if you need more flexibility to your system, you can adjust it and optimize it for nearly everything. A lot of organic, inorganic precursors are available that makes it possible to functionalize the surface, like if you need something more hydrophobic or more hydrophilic. And the most interesting part is that the systems are very biocompatible. That means that it should be very easy to integrate the microorganisms and to ensure the viability of the microorganisms in the coating material. As I said, a lot of applications are possible using gel process. Everything starts with the sol. So the sol is formed by hydrolysis and condensation of suitable gel precursors. And what we focused on was the synthesis of spherical particles and of dense coatings. The first approach was designed as an anti-mic reservoir based on two different coating systems. The first coating is a protective coating based on gel material, and this should protect the steel of corrosion. And a second coating, a porous coating, where we could integrate the microorganisms. And the idea behind the porous coating was that a high amount of the microorganisms can be integrated into the porous system. Nutrients can go into the coating, and that should ensure that the microorganisms that are integrated are viable and can produce the anti-mic components. Both systems you see here in the same image. The protective coating was very promising and showed good results. A very dense coating with high protection properties, corrosion protective properties. Here you see the porous coating. We checked both the viability of the microorganisms in the coating, and we found that they survive both the process and a long time in the coating. But a major disadvantage of this system was the application. This was, well, not that easy, and especially for the industrial process, it was, well, not upscalable from the coating technique. So we stopped this and went to the second approach, and this was designed as an anti-mic release coating. The basic idea was here to use protective coating that was working very well, and to integrate the microorganisms into the coating. And as long as the protective coating stays intact, that means there is no scratch, there is no hole, the microorganisms should be in the coating. And once a damage occurs on the surface, the microorganisms can get released and colonize on the surface and should prevent microbial corrosion. In this same image, you can see a cross-section of the protective coating. Here you have the steel, and here you have the coating. And well, this is one result that should be highlighted, because sol gel materials are often applied in very thin layers, typically from nanometers up to a few micrometers. And here we were able, as you can see, to go above this. We were able to apply up to 300 micrometers in one coating step. And as you can see, it is a very dense coating without defects, without holes, no blistering. And this is a clearly highlighted result. Well, now I want to tell you something about methods that are useful to cure those materials. Well, in sol gel chemistry, the most often used method is the convection oven in the laboratory scale, because you can, well, investigate the curing behavior, what is the best temperature, time for the curing. But the big issue is when you go into the industry, it's very expensive, because if you change your shape of your product that you want to coat, you need most often a new oven, and it's very expensive. And the curing time takes sometimes very long. Another method that we introduced, this is not very often used for sol gel chemistry, are IR emitters, infrared emitters. It's a very fast process. You can accelerate the curing process 10 times. And but you have still a few processing issues, like you have to have quite constant distance between your plate that you want to cure and the IR emitters. That means if you have something very flat like we used in the project, it's quite easy. But if you have something round shaped, you have to move with the IR emitter around, and that makes the process difficult, because if you have a change in the distance, you will have a change in the protective behavior of the coating, and that makes difficult shapes, well, not easy to cure. Other curing methods are hydrosilylation. People that, well, are familiar with silicon chemistry will know it. It's quite expensive, because you need platinum and you need temperature for the curing. Another method would be to use a co-binder, which can react with a sol gel binder, so you get a dense material if both components are mixed. Another method what we used a lot in the project was to add a curing catalyst. Acids or bases can accelerate the condensation of the material and accelerate the gelation time. This is what we used here. And another method that we used was to use other metal alkoxide to aid the crosslink, to accelerate it. And we found that titania is a useful component to accelerate the curing, and especially to get non-tacky surfaces in a very short time. As coating methods in the laboratory, often used is inverse coating, dip coating, and Dr. Blade. This was what we used at the beginning of the project, but as the project moved on, we tried to upscale our coating methods to, well, methods that are more interesting for the industry. So we use spraying, brush, and painting most of the time. And those are some images from the laboratory where we prepared the structures for the demonstrator. And spraying and painting was the most suitable method for the industry process. Brushing was possible as well, but wasn't that easy. So we have two main products, salt gel products. B1, this is oven cured material, and B2, room temperature curable material. And both materials are very similar in the composition. The main difference is the amount of cross-linked siloxane in the materials that we are using. And as you can see, both materials can be applied in very high thicknesses. The oven-cured material can be applied in higher thicknesses. This has something to do with the evaporation rate of water and other solvents that are used for the production process. Both materials can be used as a clear coat. That means you don't have to formulate them. You can do, but you don't have to. These are some results that we have selected. B1 shows the best corrosion properties, and that can be explained because applying a higher temperature than 80 degrees leads to very fast evaporation of everything what is volatile in the mixture, and that leads to a very dense material. And when using room temperature curing materials, you do the cross-linking, and during the cross-linking process the material starts to shrink, and this produces a pressure inside of the coating, and that leads to evaporation of the solvents in the coating. And if you don't use the right amount of catalyst or metal alkoxides, the shrinkage is too high, and you get a little difference in the coating behavior. And here we have the coating with the anti-mic, and as you can see, it's quite similar to the room temperature curable material. That means that integrating the microorganisms into the coating doesn't have any negative effect on the coating properties. Here we have some ice results of B1 and B2 in comparison at the initial stage of immersion in saline water and after 15 days. And here you can see again that B1 is working quite perfect. There is no increase of the resistance, and B2 has lower barrier properties but doesn't increase over time. We have more data for B1 that show that it even works well after more than 1 month of immersion. B2 is a very new generation. The last generation doesn't work that good. We will show on the next slide, I think. But the new version is working quite good. So we have a very constant barrier properties of the coatings, and that looks very promising. Here we have the adhesion, morphology, and the porosity of B1, and as you can see, we have a quite dense coating without any defects, holes, or cracks that can increase the corrosion protective properties of the material. And this material these materials B1 and B2 were upscaled and tested in the demonstrator, and as Rocio said, we tested it in the port of Harlingen, in Naples, and in the port of Gijón. And in all of those demonstrator places we tested steel coupons with both materials. In Harlingen and in Gijón we coated some other steel constructions like steel panels or steel railings that were tested in the marine demonstrator. And in addition to this, in Naples, we tested a terrestrial demonstrator. A steel pipeline was coated and buried in the ground. Here we have first results from the Gallant Marine demonstrator. On the left side, you have a control plate. Here you can see that a lot of green stuff is attaching to the surface and it's growing. And on the right side, we have a coated steel panel with B2 and the integrated microorganisms. And as you can see, there's still something growing, but the growing rate is dramatically increased. Here we have first results from the Naples terrestrial demonstrator. VLCI had attached device to check all the time the corrosion resistance of the coating, and BS2B1 to BS2B2 are the new formulations, and as you can see, they are working really good in contrast to the old one. So we can say we have developed a sol-gel derived anti-corrosion coating. We can cure it at RT or thermally. Both are working quite good, but B1 is the preferred system at the moment. No filler is necessary. That means it can be used as a clear coat, direct or metal. In case of RT, the coating thickness can be from 1 micrometer up to 300 micrometers. The coating can be applied in different layers or just in one coating step. The ice result revealed good barrier properties for both B1 and B2, and the demonstrator results are promising. And here are some scientific results that we have published. Thank you for your attention.